Now, this one here. What happens here, guys? We have our bank from river. We have the river here. Now, our boat starts off here, and what we know is that if you're looking for the quickest route is just put all your energy into going forward. Now, I just want to get a bit of technical stuff out of the way here. VBW is the velocity of the boat in still water. Are you happy with that? VBW represents the velocity of the boat in still water. So what actually happens is the velocity of the boat in still water is, 1.3. The velocity of the water, or the river, it can be also R, is going to be 0.5. Now, we're assuming we're setting up our question that it's going to be 0.5I, going 0.5 to the right. And if we want to go as quick as possible, we're just going to aim directly up. Are you happy with that? So we're going to aim up with 1.3. So the actual velocity of the boat is what, guys? If to the person observing on the bank, how fast is the boat actually going? It's going 0.5I plus 1.3 J. You will actually see, although the boat is aiming across, the river's dragging it down, and what it sees is going in that direction there. Is that alright? Now, it's a very easy question. I just had to give you a bit more language than you need at this point in time. All you need to do is, it's 39 meters across, and just divide 39 by 39 divided by 39 is going to get divided by 1.3. Because 1.3 is the velocity going straight up. So 39 divided by 1.3?
30.
30 times?
30 times,
yeah. So it's going to take 30 seconds. Now, quickest route questions are that easy, and they actually turn up in the leaving section. Okay? Now we're going to concentrate on the shortest route. Now, yeah?
It's 39 straight across and the boat ends up going to the side, is it not?
Yeah. You only have to match up the components. See, that's technically a J component. You're right. The boat does travel. The boat technically travels this much distance, yeah?
Yeah.
You are right. It travels more distance, but what happens is this 39 is how much you travel upwards. So it's the J component of the distance divided by the J component of the velocity.
Yeah.
So distance over time still applies. We'll take your one for a second there as well. What you could have done, you could get the angle and do Pythagoras' theorem and work out how far you drift across, how far diagonally you go, but it's really unnecessary. Okay. Now this way. Now guys, this one's different. Okay. So this time around, you have to go the shortest distance possible, okay? Now, in the shortest distance possible, what happens is this. You have to, in order to go straight across, what must you be? You have to be faster than, your velocity has to be faster than the current for you to go straight across. Would everybody agree with that? So, an example would be, if you could swim just as fast as the stream itself, what would happen there is that you would, if the stream's going at 0.5, and imagine your top speed was 0.5, all what you do is if you wanted to go straight across, you'd have to aim 0.5 across, wouldn't you? And you're going nowhere because you have no extra speed to go upwards. You're using all your energy to combat the current. Now, what I suggest we do as the boat this time around is, as the boat, we're going to aim in a direction, and in this direction, what we're going to do is we're aiming our 1.3 diagonally up, and its components has to be 0.5 going to the left. How do I know it has to be 0.5 going to the left?
Then you have to go further to the right. Because
you have to combat the 0.5 going to the right, so that your relative velocity just goes straight up. Now, I'm going to use Pythagoras' theorem here and find out what we call it x is. So 0.3 squared equals 0.5 squared plus x squared. It's a 13, 12, 5 triangle. It's going to be 1.2. X is going to be 1.2. Okay? So, what we now know is that the velocity of the boat in water is no longer 1.3j. It's going to be minus 0.5i plus 1.2j. The velocity of the water is still 0.5i, isn't it? Now, what's the actual velocity of the boat this time around? The actual velocity of the boat is just going to be going 1.2 upwards. Would you agree with that? It's going 1.2 upwards because the 0.5s are cancelling each other out. You're going directly up. Now let me show you how the formula links into this. Phi BW is Phi B minus Phi W. You'd all agree with that, yeah? Therefore, velocity of the boat is Phi BW plus Phi W. Everybody agree with that? Doesn't matter if moving it over the other side. And therefore, when you add them both together, you're going to add minus 0.5 plus I plus 1.2j, and then Phi W is plus 0.5i. The i's cancel, and velocity of both therefore results in 1.2j. Going 1.2 directly upwards. Okay? So this time, it's covering all 39 meters at a speed of 1.2. What's 39 divided by 1.2? 39 divided by 1.2?
32.5.
Sorry?
32.5.
32.5. As expected, it takes more time. Everybody happy enough with that? Okay. Let's go again. Now, similar question. Straight river is 50 meters wide. So, once again, you're going from 50 meters wide. Now, a boat can travel at 0.5 meters in still water. Phi BW is 0.5. Velocity of the water is 0.3. Now, let's not waste any time here. What's the speed going across? How many times the speed going across, or how long it takes to go across? You just aim all your effort upwards. So you're going to go 0.5 meters per second upwards, and what's your distance you have to cover? Sorry?
50.
50. So 50 divided by 0.5, what do we get? 100 seconds. Our quickest approach is 100 seconds. We do, however, get dragged downstream because we're using all our velocity to go straight up, and the river drags us down the side. That's the easy one. Now, here's the hard one. Is the shortest distance. Okay. So, shortest distance. Once again, we're going to have this going across at 0.3. And if I'm the boat, what do I have to make sure I do? I have to make sure I aim across to the left, and I have to combat this 0.3. My velocity I do is 0.5, and using Pythagoras' theorem, I find out this is 0.4. So this time, velocity of boat and water is going to be minus 0.3i plus 0.4j. Therefore, phi b, as discussed earlier, is phi bw plus phi w. Add them both together, and you find out that phi b is 0.4j. Divide 0.4 into 100 because you're into 50 because you're going across 50 meters. So what's 50 divided by 0.4? Anybody know?
125.
125. Therefore, my shortest time and my shortest distance differ by 25 seconds. They're pretty handy, aren't they? So far. Right. Yeah.
Can you explain the whole dB equals dB solution?
Okay. Now, the stream flows at 3 meters per second. A canoe can roll at 5 meters per second in still water. He's faster than the water, which means he has the ability to go straight across. How long would it take the canoes to go 80 meters upstream and then back again? If the stream were a still lake, it would take the same. If the stream were to be a still lake, would it take the same time to complete the same journey? Justify your answer. Okay, this is interesting. I'm going to cut it here. And I'm going to concentrate completely on this part here. Now, once again, we're going to draw our diagram of a river. Excuse me. Now, he wants to go 80 meters upstream from where he starts. So he starts here, and the end is here. Or here even. Let's go there. Okay, so he starts there, ends there, and this is the path they took. Now, this velocity here is called VC, the actual velocity of the canoes. Is everybody happy with that? That's what he actually did. Now, 3 and 5, how long will it take him to complete the same journey? Canoes can roll 5 meters, how long will it take to go 80 meters upstream and back again? Okay. Now, what we have to do at the same point in time is we don't know for sure if he's fighting the current to get there, do we? Do we know if he's just putting his head down and going straight across, or do we know that he's actually fighting the current? We don't actually know this at all, do we? No. Okay? Sorry, what I mean is... Now, sorry guys, it's like this. Sorry guys, so this one here is actually much easier than I let up. You're meant to go 80 meters upstream, it's really easy. And 80 meters upstream is really easy. You go 5 meters in still water, so your 3 meters per second is the water. This is you being the canoeist going 5 meters per second. Your combined strength is what? 8 meters per second. So it's 80 divided by 8, which equals 10 seconds. It's actually that easy, sorry about that. Now, on the way back, you're going down 5. It's still going up 3, which is overall down 2. So 80 divided by 2, 40. Your combined distance is going to be, our combined time is going to be 50 seconds. Okay, so you're going straight up and straight back down again, upstream being the key word there. Okay, and back again. Now, if it was a still lake, it doesn't matter if you're going up or downstream. It's the same time to go up as it is to go down. So therefore, this time it's going to be 80 divided by 5, which gets you 16 seconds. 16 seconds then multiplied by 2, 32 seconds. So this one here takes 50 while going up, and then straight back down again takes you 32. Because in this question here, there is no river. It's like there is no current, because it says treat it as a still lake. So it goes 32. It's 32 seconds because it's 16 for the way up, and the way back will be the same amount. Yeah. Any questions?
So they're not cancelling each other now. On the way, if it goes fast on the way and then on the way back.
What's happening is, we'll make this really easy on ourselves. Let's have the ship going directly down. The ship is going directly down at 15. There's a plank then. The plank is extending outwards from the ship at 8 meters per second. Yeah? So, technically speaking, your speed is going diagonal downwards. Would everybody agree with that? As you're going down, you're getting pushed out to the right. So then when you break this up into two components, it's 8 and 15. Do Pythagoras' theorem, I think it's going to be 289, 17 should be the answer hopefully. So X is going to be x squared equals 8 squared plus 15 squared. And what you get here? 64 plus 225 gives us 289. X equals 17. Okay.